welcome back to 7th grade science. Today we are talking about plate tectonics part 2. So far we've already talked about Wegener's continental drift theory, but at this point it's not really complete. It needs more support. This added support that was needed came from a very surprising event that occurred in the United States history, and that's World War II. Specifically, it involves the US Navy ships that we used during World War II. These ships had pieces of equipment on them called echo sounders, and these echo sounders were used to look for enemy submarines underwater. These echo sounders would send sound waves from the ship out into the ocean, and then they would bounce off of an item and come back to the ship. Since scientists know how fast sound moves in water, they were able to determine how far away the item was from the ship. And they did this by using how long it took the sound to travel from the ship to the item and then back to the ship. Did they find any submarines? I'm sure some, but the majority of what they found actually involved the ocean floor. What they expected to see was that the sea floor was just flat and featureless, just kind of like flat terrain, nothing around you for miles, except for maybe some fish and stuff like that, but no bumps, just super flat. It's kind of like Florida, flat as far as the eye can see. What they were surprised to find, though, was the flat terrain that they envisioned wasn't reality. There was actually a ton of topographical features. And what do I mean by topographical? I mean your mountain ranges, your rifts, trenches, different things like that. Another term for this is bathymetric features. Bathymetric just refers to the floor of a body of water. So in this instance, since we're talking about the ocean, it's the sea floor. So I mentioned mountain ranges. You might be shocked to find out that there are actually mountains underwater. Long chains of mountains that rise up above the sea floor are called mid-ocean ridges. And in the middle of these mid-ocean ridges is a rift zone. These rift zones actually cut the ridges into separate pieces. Now, we have mountains, but we also have deep sea trenches, which are kind of like the Grand Canyon, where you can be high up and then look way down and it's an empty space, except not on land. These are in the ocean. Some of these are near continents or near the edge of a continent, and others are found near chains of active volcanoes. Another feature we have is an abyssal plain. Abyssal plains are flat areas that may have volcanic mountains. Next up we have guyots, which are flat-topped mountains where they once had a peak but have been eroded down to a flat top. Remember that even though these are mountains, they're found thousands of feet below sea level. Aside from all of those, we also have something called a continental margin. Now, if you're working on a Word document, you have the paper area, the border around the paper that you can't type in and it doesn't print. That's a margin. So a continental margin, it's not on a Word document, but it's around a continent. So this is the areas around the continent. This is your transition area where you transition from land to deep sea. And it's made up of continental crust. More than a quarter of the ocean's basin is made up of continental margin. All of these features help explain continental drift, but the echo sounders weren't the only thing that World War II Navy ships used that actually helped further science. Besides echo sounders, World War II naval ships also used magnetometers, which were used to detect for metal underwater. Submarines are typically made out of metal, so these were another way to try and watch out for enemy submarines. Just like the echo sounders found some submarines, but also found a lot of stuff that wasn't submarines, the magnetometers did something similar. But instead of finding random pieces of metal, what they found was magnetic patterns on the sea floor, and these formed in the pattern of stripes. These magnetic stripes are stripes along the sea floor that alternate between normal polarity and reverse polarity. So in normal polarity, the north pole of the magnet lines up with the north pole of the world, and the south pole lines up with the south pole. In reverse polarity, it's opposites. That's when the north pole on a magnet lines up with the south pole of the Earth, and the south pole of the magnet lines up with the north pole of the Earth. These patterns are made up of alternating polarities. So it'll go normal polarity here, reverse polarity here, normal polarity here, reverse polarity here, and so on and so forth. It repeats. These stripes surround the mid-ocean ridges, and they end at the edge of the continents. They sometimes also end at the deep sea trenches, so it's not just the edges of the continents. But essentially, it's starting at the mid-sea ridge and then spreading out to either a continent or a trench. Now, these stripes alternate. Starting at the mid-ocean ridge, you have whatever is normal for the time. And then it lays out. So it can be normal or reverse, but on either side it's the same. And that pattern repeats itself on either side. These different stripes of polarity represent different ages of the rocks. The closer you get to the mid-ocean ridge, the younger the rock is, the newer it is. If you remember our discussion about relative age on land, where the rocks on the bottom tended to be older than the rocks on top, it's the same idea. But instead of starting at the bottom and getting to the top, we're starting in the middle and working our way outwards. So it's just horizontal instead of vertical. Something that furthers the idea of the older rock being further away from the mid-ocean ridge and the younger rock being at the center also has to do with the rock development. The mid-ocean ridge crest rocks tend to be relatively sediment-free. But then as you go out, the rocks tend to gather more and more sediments. On top of it, the crust is also very thin at the mid-ocean ridge, but as you go farther away from the mid-ocean ridge, the crust gets thicker. So the crust thickens and you get more sediments, which helps maintain that idea of the younger rocks are in the center, and then as you move outward, they get older. So if we remember our scientist, we had Wegener, who came up with the idea of continental drift. Shortly after he died, we discovered convection in Earth's mantle. Convection is when heat particles move in fluids such as liquids or gases. Down at the bottom, the particles heat up. So as they heat up, they become less dense. They rise to the surface. And as they rise to the surface, the cooler particles are more dense, so they sink down. So then you start this current, it heats up, particles go up, eventually they also cool down, and then they just come and repeat. So the idea is that in the center of the Earth, we have those convection currents happening. Why did I reference that? Well, convection currents are an important part of continental drift as well. But Wegener, who again suggested continental drift was a thing, didn't have the chance to study them. Then we enter in Henry Hess. He was a World War II naval officer as well as a geology professor. And remember that geologists are people that study rocks. He used Wegener's hypothesis of continental drift and tied it in with these new things that we learned about the topographical features of the ocean floor, convection currents, and combined it all together to help solidify our understanding of continental drift. The idea that he developed is known as seafloor spreading. So the idea of this is that hot magma from the center of the Earth rises. It rises into the valley formed from the mid-ocean ridges. Then as the lava comes into contact, because remember it's lava since it's outside of the center of the Earth, comes into contact with the water, it cools down, forming a new sea floor. Over time, more and more lava erupts at the ridge, whether it's a violent eruption like a volcanic eruption or if it's just seeping out. As it does this, the new lava that comes up is pushing the seafloor away from the mid-ocean ridge. Specifically, it's pushing from the ridge axis. And this just repeats. So you have got the magma coming up, becoming lava, cooling down, forming new rock, and moving stuff out. That's essentially the idea of seafloor spreading. But what does that have to do with continental drift? Well, it's the mechanism of continental drift, because as that's happening, then the continents are being moved as well. If you remember before, we talked about the age of the Earth, and it was approximately how old? I think I heard it, 4.6 billion years, give or take. The oldest sea floor that we've been able to discover, however, is only approximately 180 million years old. So what's happening to the floor of the ocean if the Earth is so much older? Well, as the ocean crust is being pushed out, eventually it's going to come to the deep sea trench. And when that happens, it gets pushed down in. So it gets to a certain point and then the rock just falls under. So it'd be like if I collected a bunch of stones and then tossed them into a bottomless pit. The stones of that age wouldn't be around anymore because they're in the bottomless pit. And of course, there is a bottom to the pit somewhere, but what is likely happening, or is a potential for it to happen, is at the bottom of the ocean trench is more molten rock. So then those rocks are just being recycled in the magma. So far, we talked about seafloor spreading and how it combines with continental drift. So collectively together, those two help form the theory of plate tectonics. This theory states essentially that plates are moving around Earth's surface due to the seafloor spreading and continental drift. They're explaining continental drift. Remember, convection drives the magma up, and then that magma is causing the seafloor to spread like we just discussed. Continents that sit on a plate with the mid-ocean ridge move as the seafloor gets spread. So I keep referencing plates, but am I talking about a plate like this dinner plate right here? No. I'm talking about plates made of lithograph. But before we get into that, I want to talk about another war. We talked about World War II quite a bit today and how important it was for science, but the Cold War also helped us make discoveries that tied in with continental drift and seafloor spreading. Seismometers were used in the Cold War to help detect if other countries were testing atom bombs. Seismometers measure ground shaking. So the idea was if another country was going to test an atom bomb, there would be a lot of vibrations in the earth, and they would be able to pick up on that. What they also discovered, though, was earthquakes. Because all an earthquake is just the shaking of the ground, essentially. We'll cover earthquakes in more depth later on. These seismometers locate the epicenter, which is the center of the earthquake, or it's the location on the surface directly above the center of the earthquake. When scientists took all of these epicenters and pieced them together on a map, it made an outline of these plates. And all a plate is a large chunk of the lithosphere, which we talked about the other day, remember? And these large chunks of lithosphere can carry continental crust, or oceanic crust, or both of them. So it could have just a continent, it could have just part of the ocean, or it could have continent and ocean. You've got major plates and minor plates, so the major plates are bigger than the minor plates. So to wrap things up, these theories collectively work together. We have continental drift, which is the idea that at one point we had all of our continents together as one, and over time they split up. Then we have seafloor spreading, which explains how new seafloor is formed, but as it's doing it, rocks are being pushed out. And the idea, or the theory of plate tectonics, is that as those rocks get pushed out, the plates that the continents are on are moving. So the seafloor spreading is causing the continental drift, which occurs on plates. The theory of plate tectonics is a combination of continental drift and seafloor spreading. As always, if you guys have any questions, please do not hesitate to reach out. Bye!